So I'm going to go over the architecture of the MI300A. I think it helps a lot understand the hardware you're running on, at least at a high level. So I first want to go over what I call the taxonomy of compute architectures. And everybody has this image of you have compute and memory, a basic computing system. Those don't exist anymore. You can't find a computer with just a single compute processor and a single memory. We have a lot of systems with multi-level memory, and most of our GPUs are down where in this lower right, which we label discrete GPUs. So discrete GPUs have a separate memory for the GPU and the CPU, and then you have to move memory back and forth. So you have to manage the memory. And that's the way it's been for 20 years now with GPUs. An APU architecture, which we're going to be talking about here, is where you only have one memory and both the CPU and the GPU address the same memory. So it's a single address space, single pointer. You do not have to move memory around. So it's fundamentally a different architecture. And in today, where we are in a memory-dominated era, where memory movement's the important thing, memory takes more power than anything else. And it's a significant part of the cost of a system. Having a single memory is a tremendous advantage. From a facility viewpoint, less cost of purchasing the system, and you are using less power to run it because you don't have two memories. You can also look at it from the other point of view that you have twice the memory because you're not splitting it between the GPU and the CPU. Okay, so that's the advantage of an APU architecture. And so I'll give you a little bit of history. So integrated GPUs have been around for a while, but they were fairly weak GPUs that were on the central processing unit, the CPU. And AMD bought out ATI 15 years ago with the goal of putting the GPU on the same chip as the CPU. It nearly put them out of business because of the technical challenges. They didn't realize how difficult that would be. And it took 5-6 years for them to figure out how to do that. But that was on the CPU socket, and their goal was the commodity market, that they could sell one chip and it would be cheaper than somebody who had to sell multiple chips. So it was all for this CPU market. And so while that was interesting to us in high performance computing, there wasn't enough compute capacity there. So we never really did much with it. It was, the attractive thing was that single memory would make programming a lot less complicated. But you were limited by that socket size and the power that a CPU could draw. We moved to the GPU space with the bigger form factor and several other changes that are very, very critical. This chiplet design. So each chiplet is placed on this silicon base layer. And because if you have to build a large chip like this in one piece, your yield is very low. A Knights Landing from Intel, they had a lot of yield problems because it was such a big chip. And after they sent out the first systems, they sold all the nice landing chips that didn't meet specifications at very low prices. But because we're using chiplets, we take the chiplets that pass the testing and put them on the board, we can get much higher yields. So this is a big advance in the chip building capabilities. But we also can do something interesting. We can put different kinds of chips on there. It can be either a GPU chiplet or it can be a CPU chiplet. And we have much, much more space to work with and a lot more power. Now, the CPU guys say, well, if you gave me that much space and that much power, I could build a chip too that would outperform what you're doing. But it's really that we have that much more space, and GPUs we expect to pull 500 watts, CPUs 135 watts. They're different sizes, they're different markets. And here's a diagram showing what's happening here. So you have this silicon layer there, and they're placing the chiplets on it. And this is transforming what used to be a 2D architecture, where we had all these pins down below here trying to get up into the chip. Now we have a 2.5 or 3D architecture with silicon vias going through the different layers. And the HBM memory has already got a stack of 8 to 12 memory chips with silicon vias. So you're seeing a radical change in the hardware that we now have 3D hardware. So we're building layers that gets everything closer together and improves our performance. And this was proposed at Los Alamos actually about 20 years ago, but it's just now AMD is just bringing this to the commercial marketplace. And there's more than just these compute chiplets, the XCD, which is your graphics chiplet, and CCD, which is your CPU chiplet. But you also have I/O and other supporting mechanisms built into that single silicon device. And where this came to market is first in the MI200 series, we saw 2 chiplets on that silicon layer. And the 200 series are still, I think we got 2 systems in the top 10 of the top 500 that are still based on the MI200. So competitive, even with, as an older generation, it is still beating our competitors' best offerings at that scale. The MI300A is targeted for HPC with the CPU and GPU. And you can see down here in the corner, that lower right quadrant is 3 CPU chiplets. The 300X is all GPUs, and that's more aligned with workloads such as AI and heavy solver work. So these both have the same bandwidth, and I think I show some numbers on the bandwidth, but they have the same theoretical bandwidth. The MI300X has 192 gigabytes of memory, and the MI300A has 128. So the MI300X has a little bit more memory. So that gives you the hardware architecture, but we need to think about the programming model of how we program these devices. And the programming model is separate from the hardware. So we call this the APU programming model because even when we got a discrete GPU, we can program it like it was an APU with a single memory. So it will look like a single memory to us and make the programming easier. but you still have the cost of moving memory. So for a long time, we've had this separation of, we have a host and a device. And the host is our CPU chip and our device is the GPU chip. We offload our heavy workloads to the GPU. And the GPU is very, very good if we've got a lot of work to do. It's not as good if we only have one or two things to do. And so these two devices work together to get the best performance out of your computing system. You need both of them. And you have to think about the memory model. This is often skipped over, but the memory model is crucial. When I change memory, when does it get updated? When can I access it from somewhere else? And so these memory model, the consistency is really, really important. And this is what AMD learned by making that APU 50 years ago. Why AMD has a lead in understanding how to build hardware and software that will have a consistent memory model. And anybody who has done shared memory knows race conditions are really, really hard to work through, to understand. So on these discrete GPUs, we have something called managed memory. So managed memory can be a little misleading. It means the system is managing the memory for you, instead of explicit memory management where we move the memory. And so the Linux operating system, it has built in this managed memory ability. So this is available across multiple vendors. And if you hit a page fault, you can intercept it and move the memory from the GPU to the CPU or the CPU to the GPU, which makes it look like an APU, a single memory space, even though it's two. And so you're still in this discrete GPU space where you're having to move memory back and forth, but you're letting the operating system do it for you. This allows you to write APU code on an MI200, even if your goal is to run it on a 300A. And what enables this is something called XNAC. So this is not acknowledged. It's another computer speak term, which makes no sense to anybody other than the hardware and operating system folks. But it means that the page load is not acknowledged, it fails. And so if we set this XNAC flag, HSA XNAC equal 1, that will automatically move the memory for us. And it was confusing for a lot of us. We have to set that on the APU as well. And the reason we have to set it is even on the APU, it has to populate the cache with the memory. Even though it's a single address space, it has to put the memory into the various levels of the GPU cache when it encounters that address. So typically we just use HSA XNAC. If you can't find this address, it's probably because you forgot to add that flag. And you set that in your environment. Okay, so we've moved from this discrete architecture to this single address space. And the thing that is so powerful about this, I find that some managers don't understand why we get so excited about the MI300A, and it's because it's easier to program. You can move a loop over to the GPU, and your program starts speeding up. You don't have to think about all that memory movement. that I got to move array X and array Y over to the GPU and then move it back. And having ported large scientific applications, the vast majority of the time I spent was moving the memory back and forth and trying to, who's got the most current values in this array? And it gets very, very confusing in a large physics application. So this just makes it so much easier to port and to program. Now, if you get everything over on the GPU, the discrete GPUs can perform just as well, but you've got this extra memory that you're dragging along that you're not using. And so the MI300A has certain use cases that it's very, very powerful for, and other applications, it doesn't matter as much. And in particular, the chemistry codes that never move everything over to the GPU, they find this APU programming model much, much easier to work with. So what does our APU programming model look in real code? This is with OpenMP, and we have the CPU code with our typical OMP directives for a Fortran code. And to move to the GPU, it looks a little different. We add the target clause to the OpenMP directive. And then we need the map to move the memory back and forth. With APU code, that map goes away. We do have to add this one line at the top saying that this is unified shared memory, but then we don't have to worry about memory movement at all. So it makes it a lot easier. You know, there's two aspects to GPU programming. One is parallelizing the loops over on the GPU, and the other is memory management. And here we've eliminated all the concerns about memory movement. So it greatly simplifies the programming. And then with HIP, which is our version of CUDA, you notice here's CPU code with our CPU function. Typical discrete GPU programming, you have to allocate memory on the GPU for every array you have on the CPU. And then you have to move it back and forth. Okay. In the APU code, you notice it all disappears, and we much closer to what the CPU code looked like. We just have to write that new GPU function to run on the GPU, and we may need a synchronization barrier. So it reduces all this complexity that you have with allocating memory and moving it back and forth. So it greatly simplifies the programming. With higher level frameworks, it's similar. We saw OpenMP code, Raja and Cocos code, which are higher level C++ frameworks. Again, all the memory movement is gone. Okay. And the other thing that has happened in the last 10 years is that we've gotten a much richer set of programming languages to work with. And all of them are good, and there's no one answer. It depends on your project. But we've talked about CUDA, ROCm, HIP level programming, which is close to the system. Pragma-based languages are now starting to become very effective. We're seeing sometimes where the OpenMP offloading is actually performing better than the low level in some cases. Still, you have a lot more control at that lower level. We have frameworks that working at higher level like Cocos and Raja, or many other of these higher level frameworks. And then we're starting to see standard-based languages show up. We'll talk a little bit about each of these during these next 3 days. 3 days sounds like a lot, but there's a lot of programming languages that you can choose from. It's good to know all the languages, even if you are going to focus on one, because I think it helps you understand what is being done in each language, comparing them with what another language does. You can also mix and match them. You can have one part in OpenMP and another part in HIP if you want to really dive down and try to get performance. So OpenMP is the option we suggest for AMD GPUs. OpenACC was very, very common for a while out of the PGI compiler, which became the NVIDIA compiler. It is being replaced by OpenMP by a lot of the vendors. NVIDIA is really the only company that is still supporting OpenACC. Cray has moved away from it, and partly because the OpenMP it has a much bigger community behind it. Do Concurrent is showing up in Fortran. It works right now on the CPU. We're expecting it to work very soon in our compiler. Simple loops will work very soon on the AMD Clang compiler. And that can make it much easier to do Fortran without changing a lot of your code. So AMD really supports portable programming. It's one of the reasons I joined AMD, is I really believe in portability, that we don't lock you into one hardware vendor. So almost all of our languages will run on either NVIDIA GPUs or AMD GPUs. And having worked on million-line physics codes, we can't afford a separate code for each vendor. And real applications need to have that portability. And so the heterogeneous interface, compute interface for portability HIP is actually a portability layer above ROCm and CUDA. So we'll show you an example where you can change just your makefile and it will call either NVCC for CUDA or HIPCC for our GPUs. And so it's designed to be portable. And we strongly suggest keeping that portability. So we're not trying to tell you to just write code that will run on the AMD GPUs. The higher performance portability frameworks, these have mostly come out of the Department of Energy laboratories. And their goal is a single source so that you don't have to have a different source for GPU and CPU. If we back up to the Pragma-based, they're not quite single source, but they're actually portable across languages. So you can mix and match Fortran and C and C++. You cannot do that with these portability frameworks. They really are targeted towards C++ codes. So with C++ standard-based languages, we can add a policy to an algorithm, and it will change whether it runs in serial on the CPU, or if we use this par unsequence, it will run parallel on the GPU just by changing the policy. It does take a little bit more effort to write your code in C++ using algorithms rather than loops. So it's a little bit different for those. I like to look through code and say, I know where the compute is because I see loops. And it's very confusing to me when there's a line in there that's taking 90% of the runtime and it's one line and there's no loop. But with C++, you know, they do have some of those shorthands, and by adding this policy, then that algorithm will run on the GPU, and it uses the thrust library, the rock thrust library on the back end to do the algorithm work. So that we have a couple codes that are using that for a production code because it's more acceptable to C++ code bases. It's not my recommendation right now. It's more exploratory, but it is very interesting development in C++. And with it being part of the standard, it will run across architectures. We have many other languages. They don't all get as high a level of support from AMD. We just run out of resources at some point. But Sickle will run on our system, Julia. We had a whole day of workshops on Python for AI workloads. And then many other AI packages like PyTorch, JAX, CuPy, TensorFlow, and they're pretty much drop-in replacements to run on AMD hardware. Not necessarily with the best performance at the start, but they will run, moving it from any other system to the AMD GPUs. So here we go into our training examples. So you can clone that repository, and the managed memory has those examples of the APU programming model if you want to try working through those. And at this point, let's see, I think in the handouts I gave you, there is an exercises document. Let's share that. So here are the exercises document. This is, you can, especially after the workshop, you may want to go through here and just step through all the exercises. So we first had the information on the system if you want to look through that. And then you can go to the programming model exercises. Click on that. And it will jump to each of those examples we showed in the slide, but with some of the details filled in so it will compile. Sometimes the code we show to fit in the space is not complete. So you can, here's showing a CPU code, baseline, standard GPU code example. And if you clone that repository, this code is already there for you, so you can just compile it and run it. Take a look at it. Okay, so we have a break on the schedule. We should have printed out the schedule. Where I am. Okay, if you pull up the chat, there is a question about the MI300A with 6 XCDs and HBM stacks. The way it works right now is I said you had 4 MI300As on the Perry-Peak nodes. So that's a little confusing because there were 6 XCDs, but there are 4 sockets on the Perry-Peak. So you actually have 4 MI300A sockets, each of them with 6 GPU chiplets on it. They look to you like a single GPU, okay? And the memory on that MI300A is allocated round robin across those, so alternating across the HBM stacks. And so there's about a 15% performance penalty if it's not the close HBM, and about a 30% power penalty if you don't have the local memory. There are other modes you can run the MI300AN. There is a CPX mode, which will break up the compute architecture into separate chiplets. There's a CPX mode and a TPX mode. The CPX mode is the one that is currently supported. And some of our sites, such as Lawrence Livermore on El Capitan, are experimenting with that. And they get better memory performance if they split it up into CPX mode, because now the memory is closer. But there's also different NUMA regions you have to do it at boot time on the chip, but you can have a single NUMA region or 4 NUMA regions. And so you can also do that on the chip. For general use, I would stick with the single partition, the SPX mode that most people have on their system, and the single NUMA region. And the reason is because if I if I break up the memory, I don't have access to all the memory from a single GPU. So you have to be smarter about how you allocate memory. Okay. But it is worth looking at, and we're also doing experiments about changing the way the memory is allocated across the HBM stacks, that even in SPX mode, we can get better performance by changing that algorithm where each page was on a different HBM memory. Okay, so that's actually a really good question, but that's diving deeper into the architecture. We can also, in Slurm, we can tell Slurm that each GPU there's only, on the system, it thinks there's only one GPU, but I can tell Slurm to treat it like 2. And it will allow 2 of you to grab that same GPU, but with half the memory. And because the GPUs are so fast, you will hardly notice the difference. That can be very effective, especially on the front end login node, where we want a lot of GPUs available for people to do compiling or other light workloads. So there's a lot of lower level details to this hardware that you can experiment. Okay, let's go ahead and do exercises, and I'll get ready for the next presentation at 10 a.m.